Let's get started. Today's lecture is going to be on strongly connected components. This is in your book, chapter 3.4. Let's take an example. From your book of a graph here. Let's first refresh our memory and run depth first search on this graph. And so let's see what happens. We start with A. We open A. From A, notice there's nowhere to go. So we're done with A. Then we go to B. From B, the only edge out is to E. So we go to E. And from E, the only edge is going back to B. So we wrap up in E, we go back to B. At B, we're just done there. There's nowhere to go from B. Then we go to C. From C, we go to F. From F, there's an edge to E, but that's already been visited, so we actually wrap up in F. We go back to C and we wrap up in C. We go to D. At D, our only neighbor has already been visited, so we wrap up. Then we go to E. E has already been visited. F, visited. G. So we start G at 13. We take G's only neighbor, it's I. So 14. Then I has neighbor J, L, K, and H. And from H back to G, G has already been visited. So we wrap up 19. We go back up. 21, we go to J. J's other neighbor G has already been visited, so we wrap up. Back to I, we wrap up. And we wrap up here. All right, so just a refresher on depth first search, but we're going to also be using this graph in what follows. All right. Let's another copy of the graph. That's all cleaner. All right, so what is a strongly connected component? Well, we already saw in an undirected graph the notion of a connected component. In a connected component, we say two vertices are connected if there's a path between them. And a connected component is a set of vertices that are all connected and there are no edges going outside of this set. So remember something like this. This graph would have three connected components. How does this concept apply to directed graphs? Notice that in an undirected graph, if we say there's a path between U and V, that's goes both ways, meaning we can think of the path from U to V or from V to U, doesn't matter. But in a directed graph, it does. You might have a path from U to V, but not a path from V to U. Look, for example, at C and G in this graph. There's a path from G to C. It's this one path. But is there a path from C to G? Look carefully, you'll realize there's no path from C to G. So therefore, the definition of a connected component is a little bit different for a directed graph. And in particular, we call it a strongly connected component, and we're going to define it now. Underneath is a definition of what it means for two vertices to be connected. So the definition here, U and V are connected if and only if there exists a path from U to V and there exists a path from V to U. So in other words, C and G are not connected because there's a path from G to C, but there's no path from C to there's a path from G to C, but there's no path from C to G. However, G to K, for example, there's a path from G to K, and there's a path from K to G. In fact, I'll write down that if you have a cycle property, if you have a cycle, all the vertices are connected in the cycle. All the vertices of a cycle are connected. So for example, right, if you have like you have the cycle, well, if you pick any two vertices, like X and Y, there's a path from X to Y, and there's a path from Y to X, right? Just going around the cycle. And so it's just right away obvious thing to observe. So that's why you can see there's a cycle here, and all those vertices are connected. This leads us to a definition of a strongly connected component. This relationship with this connection relationship creates a partition of vertices into what are called strongly connected components, which we abbreviate as SCC. So in a strongly connected component, all the vertices are connected, but the component is maximal in the sense that we can't add to it we can't make it any larger. We can't add any other vertices to it while keeping connectivity. Also, remember the definition of a partition. A partition is we divide a set of vertices, okay, into components with the property that the components don't overlap and that every vertex belongs to the component. That's what a partition is. The strongest connected components form a partition of our graphs. Let's look at this example here. You may have noticed the dotted circles. These are the strongly connected components. In here, there are 5 strongly connected. 1, 2, 3, 4, 5. So we can verify that they're strongly connected components. First, we check that within every component, everything is connected. Here, we already saw that this component is made up of has a cycle that visits everything. And that means that everything, all those vertices are connected. C and F are connected. B and E are connected, right? You can go from B to E and from E to B. Single vertex components are by definition, everything in there is connected because it's just one vertex. To finish verifying that these are indeed strongly connected components, we want to make sure that we can't merge any of these two together to form a strongly connected component. For example, take this big one. Can we add anything to it while maintaining connectivity? Well, you might think, look, there's an edge going out of it to E. So perhaps E could be added to this component. But notice that if you look here, if you look at edges going in and out of the component, there's only edges going out of the component. There's nothing coming in. We'll later see that this is called a source component. But here the point is that if there's nothing coming in, then I can't expand this component. I can't add anything to it because I may have a path to it, but there's no way for me to get back to any of the vertices in the component. So this is indeed a strongly connected component. We can also take a look at this guy. So is there any way to merge this with anything and still be a strongly connected component? Well, we already saw that we can't merge with this guy. We can't merge with this guy because you see, this is what's called a sink node. There's nothing going out of it. If there's nothing going out of it, there's no path from A to anywhere else. So that means we can't merge this guy and this guy together because then A will not be connected with B or E. The opposite is true of merging B and E with D. So we have a path going out of D to B and E, but we have no path from E or B into D. In fact, nothing goes into D. Any questions at this point about the definition of a strongly connected component? Yeah. That's a great question. I think you're right. I don't want to bet my life on it, but I think you're right. Other question? It's important that you stop me here because if you don't understand the definition of a strongly connected component, then we're in trouble for the rest of the lecture. Yeah. Why not merge these two? If we do, is there a path from E to C? There's no path from E to C, right? You can see here, if you look at edges going in and out of here, there's edges going out to this component, and there's edges coming in from this component. But as we already saw, there's no way, once we're in this component, there's no way, there's no way to get into here. Now, this is a source component. There's no way to get into. Yeah. if D was off by itself, it would be a strongly connected component. So for example, if I put a, having trouble finding a letter, let's say a P, right? Let's say it's just off here, then this is its own strongly connected. Because remember, strongly connected components are a partition of the graph. So every vertex has to belong to a strongly connected component. And a single vertex is by convention always connected. It's just connected to itself. Does that answer your question? Yeah. What? Is every directed graph undirected graph? So we don't think about strongly connected. We don't apply this definition of strongly connected components to undirected graphs. For undirected graphs, we had the old definition of being connected, like here. And this was a simpler definition. Right. Yeah. It's Gij, right? Gij. Okay, why isn't Gij a strongly connected component? Because it's a cycle, so everything within it is connected. Let me be specific. What if I'm circling, what if I told you that these were the strongly connected components? What would be wrong with that? It's essentially your question, I think, yeah? Yeah. That's right. I can make a bigger strongly connected component by merging this and this. And let me give you, in fact, even simpler. So this is not a strongly connected component because L and H are not connected. There's a path from, no, I'm sorry. They are connected. So the answer is, as you gave, we can merge these two guys together. And the reason is, like, if you have a cycle in here, so everything in here is connected. Everything in here is connected, right? Like H to L, there's a path from H to L. They're connected. And then there's an edge going out of this of the right component into the left component, and an edge going out of the left component into the right component. That means that I can get from any component, from any vertex on the right, I can go, like, let's say this vertex, I can make my way to the kind of leaving point, go across, in here, find my way to the leaving point again, come across. And now I have I will have a cycle, this is the cycle again, that connects all the vertices. And so the short answer is, this is not strongly connected components because we can merge the lower two. Yeah. Let's see. So put an edge from A to D. Let's see what changes. All of a sudden, yeah, this is, so now I can find a cycle, like this is a cycle. So I can tell you then everything there is connected. So I can actually, that edge would allow me to merge those components together. Say it again. if the whole graph is a strongly connected component, or just to see if a part is a strongly connected component. So I don't know if there's a simple answer for that, but we're gonna, I think, we're gonna give an algorithm to find the strongly connected components in the graph, and I guess the answer is to run that algorithm. Right. But hopefully you get some more intuition, at least after seeing the algorithm. Other questions? All right, great. Now, there is something called a metagraph. Metagraph. I'll write MG. And the metagraph is this guy. Let me copy it. Right, so this is the metagraph. So you guys see what's happening here? I've created a vertex in the metagraph for every strongly connected component of the original graph. So we've got 5 vertices in here, and inside each vertex, I've written down the vertices in that, what belongs to that component in here. Right, so like B and E is this guy and so on. What about the edges? So I'll give you a formal definition in a second, but informally, imagine I've taken each of these guys and just squished it all, merged it all together, but I've kept the vertices going out and in to this component, but the whole component I squished into a single vertex. I have here, notice then the edges going between the components. Right, these are all edges going between the components. Those are the edges that carry over into the new graph. So let me do this one by one. So the edge going from B to A is now here the component of B to the component of A. Edge going from C to B is from the component of C to the component of B. Edge from F to E is from the component of F to the component of E. We already have an edge there, so we only have one edge that we put. From G, we have an edge to E. So from the component of G to the component of E. And we have from H to F, so the component of H to the component of F. What did I forget? I forgot from D to B, the component of D to the component of B. Let me write that down formally. Metagraph MG. Each node is a strongly connected component of G. And edge C1, C2, there exists an edge C1, C2, if and only if there exists a vertex U1 and C1, there exists a U2 and C2 such that U1, U2 is an edge. Yeah, well, is an edge in G. In other words, there's an edge from this guy to this guy because exists a vertex in this component, in particular H, and there exists a vertex within this component, in particular F, so there's an edge from H to. Question? We wouldn't have two parallel edges. All right, does this metagraph have a cycle? Could it have it? So this one doesn't. In general, could a metagraph have a cycle? How many of you think no? All right, we can go home, I guess. Okay, so it's good. You guys have the right intuition. Why not? Anybody want to volunteer? Yeah. Because if you have a cycle in the metagraph, you can then combine those components in the cycle into one bigger component. Metagraph is a DAG, basically, no cycles. So, for example, if you had a edge from D to A, right? That means you would have had an edge from D to A in the original graph. And so this, I'm sorry, that's a bad example because D to A doesn't create a cycle in the metagraph. What would create a cycle? A to D, good. A to D. So A to D, let's say we have that. So then we would have to have this edge. So that means that if we have this cycle of components, we will have a corresponding cycle in here. Let's say we add an edge from like this. And let's say that's this edge right here. That's actually, so that there becomes trivial cycle, just this one. And that corresponds to this one. So what that means is now we would be able to merge these two guys. Because remember, if we have a cycle between G and E, once we get into a component, we can go and visit everything in that component. And once we get in this component, we can visit everything in that. So having a cycle between G to E means that you actually can merge both of those. Yeah. I would also create a cycle, this cycle like this, right? So that would correspond. So to get this cycle, it's a little, it's maybe more interesting. So because from E, you can go to G, but it's not like from G, you can go to C or F directly. You have to take the path through the connected component, come to F, and now here you have an edge to. Question? I want to make an observation, and this is really kind of a deep observation. It's not a theorem or something, but just a way that we think about these things. Every digraph has a two-layered structure. It's just a way of thinking about the graph. So we have this graph, and then its metagraph. Of course, the metagraph doesn't contain all the information about the original graph. You can't, if I don't show you this, you can't reconstruct it from the metagraph. But the metagraph already tells you kind of a higher level resolution things, at least in terms of connectivity. So if you don't see this, but I ask you, is there a path in the graph from L to A? You can answer it using the metagraph. I ask you, is there a path from A to L? You can answer that using the metagraph. Okay, so now we get to our, oh yeah. It's like zooming out or zooming in. So you can think of this metagraph as a zoomed out version of the actual graph. Every digraph can do that because every digraph can be decomposed into strongly connected components. And so every digraph has a metagraph. Is it possible to have an undirected graph and a directed graph all in one graph? Yes, it's something called mixed graphs. People study those, but we don't cover that in this class. Maybe that's a good aside. So what is the metagraph of a DAG? We had before, here was our DAG that we looked at quite a bit. How many strongly connected components are here? Yeah, 6, correct. Every single vertex is a strongly connected component. Why? It's actually always going to be the case for a DAG that its strongly connected components are just single vertices. You have more than one vertex in a component, then you'd have a cycle. As soon as, for example, here, you have 2 vertices in a component, you've created a cycle. So the answer is the same graph. The metagraph of a DAG is the same graph. I don't think we need that fact anywhere, but that's just an interesting observation. And the fact that it's, so going back to the general case, the fact that this metagraph is a DAG is nice. As we mentioned earlier, DAGs are easier to work with in many ways than regular DAG graphs that have cycles. Okay, so now the computation problem we're going to solve is label each vertex of a digraph G with its strongly connected component number. In other words, find the strongly connected components of a graph. All right, so before, I mean, this is a trickier algorithm than some other ones we've seen. So before I just blurt it out, we're gonna take some time to build some intuition. If let's say I look at the metagraph, and I'm going to call these vertices here sinks, sources. Source, so no incoming edges. And sinks, this is a sink, no outgoing edges. This is a general term used for graphs, sources and sinks. What if I take run explore from one of the vertices? This is, remember, for undirected graphs, this is how we found connected components. We started an explore from a vertex, and we knew that in that explore, we would discover everything, exactly everything in that component. What if I run explore here from, I don't know, from, let's say D? Am I going to find vertices just in that strongly connected component? I run explore from D, I'm going to find things outside of that. What if I run it from A? If I run it from A, then I will explore A. I will explore everything else that maybe is in this component, but because it's a sink component, so I have no edges coming out of it, I will only explore the vertices in that component and nothing more. So that leads us to the idea run explore from a sink component, from a vertex, run explore on G from a vertex in a sink component. Then anything in that explore we mark as, okay, this is the first strongly connected component. So here, let's say we run it and we put a 1. Oops. We put a 1, we say, we ran from A, we explored everything from there, we marked it with 1. And now let's remove A from the graph. We're not actually going to do this in the algorithm, but conceptually, this will give you the intuition. Let's say we remove A from the graph. Then we have a new sink in our metagraph. This case will be B and E. So let's start from a vertex in this new sink. We repeat what we did before, but now we've removed what we found, we removed it from the graph. And now we look at the sink component BE and we start from some vertex in there. So let's say we start from B. We mark it with 2 because we're now starting the second round. And from B, we explore, we get to E, so we label that also with a 2, and that's it, right? From there, we don't go anywhere. Again, notice we didn't get out of our component. We explored everything in our component, but we never left because this is a sink, so we have no way out. All right, so we remove this. Now, and we remove this. Now the remainder of the graph, we have D became a sink and CF became a sink. So let's run on D. We'll run on D. D is a sink now. So we'll start here. Notice out of D, everything else has already been explored. Right? So we cannot leave the component. When we're done with D, we cross it out. And now we're left with CF. So let's say we start with C. This is the next component now, 4. We go to F, that's 4. And now notice we can leave C and F to go to B and E, but those have been already visited and deleted from the graph. In fact, we're not actually going to need to delete anything. We just have marked it visited. All right, so then we're done with C and F. And C and F, and we only have one component left, so we run from G, and now we can mark everything. Yeah. Absolutely. So D and CF, we had a choice. So we I think did D before CF. We could have done it the other way around, and then the numbers would have changed, which is totally fine. These numbers are not they don't have to be those numbers. So as long as everything within one component has the same number, and that's the only place that number appears, then that's fine. Right? We don't actually, so in other words, we don't care about the actual number. We care about the partition that this number generates. Yeah. That brings us to the next point. But other questions first? Okay, so I told you that this is just kind of an intuition, and it's not exactly the algorithm. So there are two challenges here. So the first is, as you asked, do you need the metagraph to run this? Now, according to what I showed you, yes, I used the metagraph to know what is a sink component. But our algorithm doesn't know the metagraph. If I knew the metagraph, I've already solved the problem of finding the components. Right? So metagraph is something conceptually that I used, but I was kind of cheating when I was telling you this. My algorithm doesn't know the metagraph. So I need to find what I need from the metagraph is I need to find a vertex in the source, in the sink component. That's in the end what I need to do, and I'm going to find a way to do it without the metagraph. So that's one. Yeah, that's the major. That's the part that we now have to figure out. So let me finish up this intuition. We run explore and G from vertex in the sink component. Mark everything visited with a distinct number. Remove visited nodes from the graph. Again, as I mentioned, we don't actually need to remove them. It's enough that they've been marked visited. And then we repeat. The key is that this sync component, though, is now with respect to this, to the new graph, after we've deleted the vertices. Okay, so let's get to the main question now, is how do we find this sync, a node in the sync? I'm going to answer something else. I'm going to tell you how to find a node in the source. Then I'll show you how we can use the same trick to find a node in the sync. Okay. So let's think now for a moment how to find a node in the source. Without looking at the metagraph. I have the following claim. Suppose I run DFS on G to get post numbers. These post numbers, right? That's the things that we got here. So let's say I have those. Okay. Let C and C prime be two strongly connected components of G such that there exists an edge from C to C prime in the metagraph. Right, so very simple. I've got some component C, I've got some component C prime, and I've got an edge between them in the metagraph. Then the highest post number in C is bigger than the highest post number in C prime. I'm relating here the DFS on the original graph, the post numbers from there, to edges in the metagraph. And in particular, I'm saying, let's say if there's an edge from C to C prime, if I look at all the post numbers in C, and I look at all the post numbers in C prime, then the highest post number in C is higher than the highest post number in C. Let's see an example. Let's take from, give me your favorite edge. What's your favorite edge? Or you love them all? A to G, I like that one too. Wait, A to G? There's no A. H to G. No, okay. No, I meant in the metagraph. What's your favorite? So there's less to choose from. G to E. G to E. So this one, right? Okay. What's the highest post number in the component of G? 24. 24. What's the highest post number in the component of E? 6. Okay. So that checks out the highest post number in the from vertex is higher than the, from component is higher than the highest post number in the two components. So let's try to extend that to a proof. Why is that the case? It goes back to the way DFS works. Now, DFS is exploring stuff, and at some point, it hits a vertex either in C or C prime, the first vertex it hits. Let U be the first discovered vertex from C union C prime. There are two cases we consider. The first case, 1, U belongs to C. So U is in here somewhere. Okay, then, what do we know about explore? If we're exploring U, we're gonna reach everything that's connected, that is reachable from U. We're gonna explore everything that's reachable from U. In particular, there is from U, there is a way, some path to get to this vertex, which is at the edge, and then we can jump to C prime, and in C prime, there's a way to visit everything else. And only then can we be done exploring U. In other words, we're going to be done exploring everything in C prime before we're done exploring U. Write that down. Then all of C prime gets visited before U wraps up. So post U is higher than post of anything, of all vertices in C prime. And that's what the theorem, that's what the claim says. And so in this case, right, if we hit C first, then we're actually going to finish all of C prime before we finish our vertex in C. So there we're good. And then we go to case 2, U in C prime. In other words, the first vertex we discover is in C prime and not in C. Right, then it looks like this. There's an edge here, and U lies in here. Now, remember that metagraph is a DAG. There's no cycles. In particular, there's no way, notice there is no way to get from U to anywhere in C. Because if there is, we would create a cycle. That means, so U wraps up. Excuse me. The other point is that when we're exploring U, we will visit everything that's reachable from U. We will visit all of C1. We visit all of C1, by the time, excuse me, not C1, C prime. We visit all of C prime by the time we wrap up U. So post U is the highest post value in C prime. Yeah. In case one, U is in here, is in C. So if U is in C, then we do go to C prime and we go to all of C. But if U is in C prime, then we have no way to go back to C. So if we're starting from U and C prime, we're just going to explore this. If we're starting from U in here, then we're actually going to explore all of this and all of this before we're done, and maybe even more. Because there's no way you cannot get from this component back to that component. If there was some way to do it, that would create a cycle in the metagraph. So you cannot get from U back to C. So that means that we're going to wrap up C prime before we're done with U, and then U will have the highest post value in C prime. But C hasn't even started to be explored, right? We assume that U is the first vertex in C and C prime that we hit. That means we haven't hit C yet. But C has not yet been explored. So all of post values in C will be larger than post U. End of proof. And so again, just to recap the claim, I have an edge from a component C to a component C prime in the metagraph, then the highest post number in C is higher than the post number in C, any post number in C prime. Any questions? So we wanted to find a vertex in the source component without looking at the metagraph. And this is going to let us do it. How? What can you say about the vertex with the highest post number in all of the graph? So here we see it is G, it's with 24. It corresponds to, it's a vertex in a source component. That's not a coincidence. And the claim we just proved tells us why. Because if this wasn't a source component, if you had some edge going into it, then you would have a post number higher than the post number of G. So let me repeat again. If I take the vertex with the highest post number, I'm guaranteed that its component is a source. Because if it wasn't a source, I would have an edge going into it. And then by our claim that we just proved, there'd be a vertex in here with a higher post number. But that can't be because I already chose the vertex with the highest post number in the graph. Let me write that down as a corollary. The node with the highest post after running DFS on G is in a source component of G. And now this answers, this gives us a way to find a remember for our algorithm, we wanted to start on a vertex in a sinc component. But the problem was that we didn't know what was a sinc component because we didn't have the metagraph. Well, now I almost solved the problem for you. I gave you a way to find a vertex in the source component, not sinc, but we'll solve that problem later. A vertex in the source component without knowing the metagraph, just by running depth first search on G, taking the vertex with the highest post number, that guarantees that this is a vertex in the source, in a source component of the metagraph. Now, okay, now about this sinc. We actually need to find a vertex in a sinc component. All right, so this is where the reverse of the graph becomes useful. What happens when I reverse the graph? Where to go? What I mean when I say reverse the graph, I mean flip the orientation of every edge. Okay, so let's copy this. Let's put it here. Let's take from your book. Let's take from your book the reverse of that graph. And let's also put the metagraphs. This is G, this is metagraph of G, this is G reverse, and this is metagraph of G reverse. Right. So let's verify that these two graphs on the left are indeed reverses of each other. Right, so there's an edge from B to A here, it's flipped the other way. And the same for everything else. From F to E, there's an edge from E to F. This cycle here is going in the opposite way. So yeah, that's the flip. What happens to the what happens to the components in the graph of the reverse? They don't change. They don't change because two vertices that were connected in a graph are still connected in the reverse graph. If there is a cycle in a graph, that's still a cycle in the reverse graph. It's just going the other way. So things are still connected. The connectivity doesn't change. So the vertices, that means the vertices are the same in this graph as they are in this graph. What about the edges? if you notice, the edges change direction. That's, again, something that just follows from how we've done the reverse. So the reverse, this meant this this edge meant that there was an edge from B to A. Well, now there's an edge from A to B. So it goes the other way. So the observation here is that the metagraph of G reverse is equal to the metagraph of G reversed. So the metagraph of G after it's reversed is the same thing as taking G, then its metagraph, then reversing it. And so we can either go like this or we can go like this. What about sources and sinks? Observation. Ooh. Source in metagraph, well, let's just say source component in G becomes a sink component in G reverse. And the opposite is true. And sink component in G becomes a source component in G reverse. Now, this is the connection we need, because now to find a vertex in the sink component of G, I just need to find a vertex in the source component of G reverse. So this is another corollary. The node with the highest post after running DFS on GR is in a sink component of G. Now I can give you the algorithm. Now we have all the pieces of the algorithm. DFS, single connected component on G. So the first step is we need to compute GR, the reverse of G. And your homework asks you to give an algorithm how to do this in linear time. Then we run DFS on GR and record post numbers in array, we'll call it post R. Yeah. Well, as, for adjacency list, you can do it in yeah. So I'm assuming for adjacency list here, and then n plus m, that's linear time. So in graph algorithms, n plus m is linear time, because that's the size of your input. That's the size of the adjacency list representation of the graph. Okay. And now we have basically, we write the rest of the, like, similar to the way we did DFS. There are only two things. One is we keep track of this SEC counter as the current strongly connected component. Then, just like before, we have to initialize for all vertices V. We set visited V equal to false. And then we have the same for loop for all V in V. Well, for all V in V. And now this is the important part. We have to, the order here is important, right? That's what we've been talking about. We need to go to the highest post number first, and then continue iterating in decreasing order of post. Decreasing order of post R. And this is key. And inside here, just as in the regular DFS, if not visited V, then we explore it. And when we're done, we increment our counter ++. And that's it. Within the Explorer, when we visit a node, we always we mark it with the current value of the component counter of SCC counter. So this puts together everything we talked about, that we need to run Explore starting from the highest value of post R, visited stuff, label that as the strongly connected component. And next, remember we were taking what's now in the remainder of the graph, the sync component. Right. But that's effectively, we can do that without really recomputing anything. We just take the next highest post R value. So let's look here. Let's look at what we do in this algorithm. This is actually this is into A, so we're going to move it here. Let's run algorithm on this graph, for which we already computed. Okay, so in our case, G is this graph here, and the reverse is the one above, and that's the one we were looking at earlier, and we ran DFS at the beginning of the lecture, and we got all the post numbers. So we start with the highest post number, so here G is the post, and we run from G, we label it with 0, and we explore everything from there. And that's it, we can't go anywhere else. Right? Then we take the next highest post, so 23, but we've already visited it, so all of these guys are visited. So the next thing we hit is D, 12. So we're going to put a 1 here. We are done exploring D. So we take the next highest remaining post, and that's going to be 2, 6, 10, 2, 6, 10, 5, 9. So it's going to be F. C. So we give C a 2. We explore from C, we can get to F, and that's it. Notice we're not going out of F because everything out of there is visited, just as we designed it to be. then 10, then we find 9 is already visited. Then we have B, which is 6. So we take B, that becomes 3. Going to E, and again, nowhere out of there. And finally, we have A. So that is the example. The final thing is the running time here. Before you go, the running time, this from your homework, the compute G of R is theta n plus m. Running depth first search is n plus m. And this is now, it's your regular DFS in terms of running time. I mean, we just added these counters, right? And we changed the order, but it's, the structure is the same. So all of this total time to find strongly connected components is linear. Right? And this is, as I started this chapter, I said DFS has many, many uses. And so here you have an example. Well, you're actually running DFS twice, right? You're running initially on the reverse graph, and then you're running it on the original graph. It's a more complicated way of using depth first search to show just how powerful it is. Any questions? Yeah. We don't return, well, we can, it's implicit. We label every vertex with the counter. So that's implicitly what's returned. Yeah. That's another, actually, that's something on your next homework is how to do that efficiently. All right. Yeah, if you have any questions, you can come up because we're over time.